This video is about vertically opposite angles. There are two sections to the video. The first section is about discovery learning and good questioning. The second section is about generalizing through questioning and algebra sense making. The rationale for the approach comes from the syllabus. Discovering the theorem for themselves is a very important starting point for students. At a later stage, the theorem can be revisited so students can gain a more formal understanding of the theorem. This will be looked at in the second section of the video. It's good practice to tell students what the aim of a lesson is, so you could have the following at the top of the board. And then say to students that today we're going to discover something about the properties of intersecting lines. The task you could give students is to draw two intersecting lines and measure all the angles, and then ask them to repeat step 1 and repeat step 1 again. They might form diagrams something like this. One could also pass around some geostrips or get them to use two pieces of paper and just rotate one piece of paper around just to see how, as you rotate one piece of paper, some of the angles get bigger and some of the angles get smaller. And it's the same thing with the geostrips. As you adjust one part of the geostrips, the angles formed will change. The key question to ask students is, what relationships did you discover? Possible student responses for this could include: the angles opposite one another are the same or are nearly the same, because sometimes students will measure an angle 57 degrees as 58 degrees and there will be some measurement error. They might say the pairs of angles are the same, or the angle on the left is the same as the one on the right and the angle at the top is the same as the one on the bottom. Or in my drawings are two big angles and two small angles. All of this is getting to the heart of the theorem we're trying to get the students to discover. Some students might say that in my drawings the angles beside one another add up to 180 degrees. Now this isn't exactly what we're looking for, because we're looking for the vertically opposite angles to be the same, but this will be very, very useful to keep in mind when we are going to prove that vertically opposite angles are equal in measure. It's a good idea to have some extra questions planned out in advance in order to further the learning. Examples of these questions could be, as one of the angles increases, predict what will happen to the other angles, or predict what will happen when one of the angles is 20 degrees, 130 degrees, or 90 degrees, or what do all the angles in the diagram add up to. Other questions could include, how many obtuse angles can there be when two lines intersect, or how many acute angles can there be in the diagram. And the one last one there will be, do you agree with the statement, when two lines intersect there will always be two acute angles and two obtuse angles? Explain your reasoning. The video at the top of the slide there is from a file that's on the student area of the Project Maths website. It's important for students to verbalise what they discover, but when students are ready, you can show them the precise language of the theorem. It's important to keep in mind the concepts of inductive and deductive reasoning. We don't want our students thinking that just by looking at a number of examples that they've proved that vertically opposite angles are equal in measure. We want them to understand that it is deductive reasoning and deductive proof that what is required to make sure that they have a watertight proof. In section 1 we use questioning to help students gain an intuitive understanding of vertically opposite angles. At a later stage we can return to the same theorem and use questioning to help students gain a more formal understanding of vertically opposite angles and to even prove why vertically opposite angles are equal in measure. Using questions similar to the ones on the slide, students should be able to see that there's many pairs of angles that add together to be 180 degrees. If we just use some algebraic symbols, it becomes easy to write down these relationships and communicate our understanding to the people in the room. So we can see that the measure of the angle ABE plus the measure of the angle ABC is equal to 180 degrees, because we have a straight angle, and also that the measure of the angle ABC plus the measure of the angle CBD is equal to 180 degrees, because there's also a straight angle in that part of the diagram. We can also write down a new relationship then and use algebra to express that relationship. So the measure of the angle ABE plus the measure of the angle ABC is equal to ABC plus CBD. And this equation can be simplified to write down that the measure of the angle ABE is equal to the measure of the angle CBD. Similarly, it can be shown that the measure of the angle ABC is equal to the measure of the angle EBD. So the questions above could be used to help students to generalise, and writing down the proof using some symbols and making it explicit to students that these symbols are helping everyone make sense of the situation means that algebra is used as sense making. This slide has other questions that can be used to help students to think and generalise about certain shapes and diagrams, both within geometry and outside of geometry. In summary, in section 1, we looked at discovery learning and good questioning, and in section 2, we looked at generalising through questioning and algebra sense making.